Okay, this is my code for my auto straight program, and just kind of going through it. We have the pragma config files or lines of code up here, which set my motor ports and my encoder ports, and then down here I have some variables that I've defined, some constants, the wheel diameter, and then calculate the wheel circumference, and then the tick constant is how many ticks per rotation there are for the motors that I have. And then I have a variable called motor speed that's currently 127, and this is the variable that I'm going to be changing with my P loop. So I'll just kind of run through the code so you can understand what's going on. Here I reset my integrated motor encoders to 0, and then while those encoders are less than 3000, it goes into this auto straight loop. So it just compares the motor encoder values, and if one is smaller than the other, then it speeds that motor up and stops the other one, so it can auto correct. I'm actually going to change these motor speeds to motor speed divided by 2, so they run at half speed instead of fully stopped. I recommend putting them at fully stopped so you can make sure that it does auto correct, because when you're looking at the debugger window, it's really easy to see a 0, and you can hear the motor start stop start stop start stop, and then adjust that speed accordingly. And then if they're equal, they both go at the same speed. And then once both encoders hit 3000, then it kicks out of this while loop and stops both motors. So again, we want to slow it down as it approaches this 3000 speed. So in my code, I'm going to add my P loop right in this spot. Again, it needs to be within the while loop for it to adjust. If it's not in the while loop, it'll only be set once. And this is the auto straight code from there to there. So again, if I look at what I came up with in the video 1 and just type in those equations, that's all I'm going to be doing. So if the sensor value of the encoder, so this is in motor encoder, and again, because this is an auto straight, those encoder values should be really close to the same thing. So I'm just going to pick one of them. I've had some students in the past that will take an average of the two, and again, that's fine. But again, I'm just going to simplify and just use one. So if it is less than 2000, we said that we wanted our motor speed to be a value, and then if it's greater than 2000 or 2000 or greater, we want it to be something else. So that's where this comes in. So at this point, I'm going to copy this and copy and paste, and I don't need the int because I don't need to declare that. So if it's less than 2000, I want my motor speed to be 127, and if it's not, I want it to be an equation, and that equation was negative, and then the sensor value of my left motor divided by 30, and then plus 127. I'm going to go ahead and save that. So this is what it should look like to get the graph that I looked at last time. And if you're unfamiliar with that, I'll show you here. So this would be if it's less than 2000, then it's at 127. And when it's 2000 or more, it jumps down here to this line, which we've set up as this equation right here. So again, you can pause the video if you need to take a look at that again, but that was video 1 where we had this set up. So all I did was I took this that I'd handwritten, and now I've put that into my actual code. And this works great. The next video that we're going to do is actually going to change this value here to a variable. Alright, so watch VEX P looping 3 for more information on how to adjust this for a variable. And then once we change it to a variable, we're then going to modify it for an actual distance in inches.